Are you struggling with parametric equations and finding the length of a curve? You're not alone. Today I'm going to show you how to properly evaluate these problems and show you step by step on what to do and how to use the formulas. Let's get into it. Hey everybody, and welcome to another lesson. Today we're going to be talking about arc length defined parametrically. Now, as you've known and we've seen in our previous videos, we can show where an object is and now when an object is. And that is, in a sense, the parameter from the parametric equations. So today we're going to look at arc length. Now, if you have a smooth curve with 2 points, A and B, that's not at the same point T, we can go ahead and find the distance between those 2 points with the arc length formula. S is equal to the integral from A to B as the square root of dy dx dt squared plus dy dt squared with respect to dt. Let's get into it. So we've seen parametric equations of a particle that's moving on a plane C. Now we're going to show you how to evaluate the distance of that path. And here's the proof. Now let's assume you have a function y equals h of x of the interval from a to b. Let's look at the arc length, and we're going to set that equal to s. We know the formula for an arc length of a curve C is defined by this: the integral from a to b of the square root of 1 plus h prime of x squared dx. Now we're going to change that to an implicit writing. Now, we know that parametric equations are easily written implicitly. Now, we can assume that C is represented parametrically by the equation x equals f of t and y equals g of t from a to b, and dx dt is not equal to 0. Because if it's equal to 0, then we're going to divide by 0, and you can't do that. Now let's go ahead and rewrite the equation. And we're going to write in the parametric equations with respect to their specific derivatives. X equals f of t and y equals g of t. So when we take those derivatives, it's going to be respect to t. Now we can go ahead and put them under the same denominator. And as you can see here, it becomes dx dt squared plus dy dt squared all over dx dt squared. Now we're going to multiply this equation by dt over dt, and when we do, we can shift it around to be dx dt over dx over dt. Now when we put that in, it's going to cancel out dx dt squared in the bottom. Now we can just have this equation here, and we can rewrite that as f prime of t plus g prime of t. And both of those squared with the sum individual in the middle and all under the square root. Let's look at an example. We're going to find the length of a curve defined by x equals t cubed minus 3t and y equals 3t squared over the interval from 0 to 1. Now, if you remember from the formula, it's going to be, we need to find the implicit derivatives of each specific parametric equation. So let's do that quickly. We're going to find dx dt is equal to 3t squared minus 3, and dy dt is equal to 6t. Now we're going to square each one specifically. Now it's going to be 3t squared minus 3 squared, all squared, excuse me, and 6t squared. So we're going to look at it, and we're going to use algebra to use FOIL to combine like terms. Once we do that, then we can go ahead and combine the equations, add, subtract common things, and we're going to get 9t to the fourth plus 18t squared plus 9. Okay? Notice that we're going to have a perfect square. This is nice because when we place it in to the square root, it's going to cancel out. So it's going to be using the tic-tac-toe method. We're going to have 3t squared times 3t squared equals 9t to the fourth, and 3 times 3 is 9. When we use catty corners, we're going to do 3t squared times 3 equals 9t squared, and the bottom left to the top right, 3t squared times 3 equals 9t squared, and the bottom middle, we're going to sum up the middle. We're going to 18t squared, which is the same in the middle. So we have a perfect square. Okay, now it's from the interval from A to B, and we're going to plug that into the formula. Now, once we plug it into the formula, it's going to be easy to notice that we're going to be able to take that out. I've shown that step by step here, and we can go ahead and use this to our advantage and just integrate 3t squared plus 3 and get 3t cubed over 3 plus 3t bar 0 to 1. Now, if you notice, 3's cancel out in the first part of the equation, and that becomes t cubed plus 3t bar 0 to 1. Now we're going to do top minus bottom, and we're going to get 1 plus 3 minus 0 plus 0 is equal to 4. And that's how we find the arc length parametrically of a curve from A to B of two functions, x equals f of t and y equals g of t. Now let's go ahead and let's find another example. As you can see here, this is going to find the length of a curve y equals ln of x on the interval from 1 to e cubed. Now, if you notice, this is not defined parametrically. So we can just find the derivative and plug it into the other formula that we have. And when we do that, we can get an answer into our calculator to be 19.5278. I hope you learned something. If you have any questions, go ahead and put them in the comments. I'll address them, and I appreciate all your support. Thanks. Thanks for watching. I hope you learned something about finding the arc length of parametric equations. As always, smash that like button and subscribe. You can find me at patreon.com searching Algebra Hero. Thanks.